All right. Now imagine getting that F statistic over and over and over again from a population and plotting a sampling distribution of F statistics. What would you get? Well, remember, the F can't go below 0, right? Because both numbers are going to be positive, right? So the F really stops at 0. But this is what the F statistic ends up looking like. This is a skewed distribution. And it has a positive tail. That means it goes for a really long time on the positive side. It's one-sided, so it's not symmetrical. It's actually asymmetrical. There's only a positive side. And it's because it's a proportion of variances. And variances are positive, right? And like T, it's a family of distributions. And you're going to be able to find the particular F distribution you're working with by looking at the degrees of freedom in the numerator, the one about between sample differences, and by looking at the denominator, the sort of leftover or within sample differences, right? Variation. So you're going to need both of those numbers in order to find out which F statistic you're working with. And in Excel, they'll actually ask you for the degrees of freedom for the numerator and denominator. Now, let's talk a little bit about what alpha means here. Alpha here, it will still need a cutoff point, so critical F instead of a critical T or Z, right? We'll still need a critical F, and the alpha will still be our probability of making false alarm given that the null distribution is true. This is the null F distribution, just saying, right? And the alpha would be the same thing, the probability of false alarm. So once you know what that alpha sort of, how you sort of can picture that alpha, let's talk about what that alpha actually means, right? If you go back to the original idea for the alpha, the original idea is this cutoff score. Cutoff level, right? So it's our level of tolerance for false alarms, right? How the probability, the false alarm probability that we will tolerate, right? And so we want alpha to be very, very low, right? Now, our alpha will be low, right? That's a smaller alpha than this one, right? Our alpha will be low if our critical F is very, very big, right? And what does it mean for F to be large? Large F. This means our between sample variability, is greater than our within sample variability. Right? And that's what it means. And so as long as this is much larger than this, we have a large F, right? And that's going to mean a smaller chance of false alarm, right? Now the alpha is the cutoff level that we are going to set as the significance level, the level that we will tolerate. So what is the p-value? So the p-value will be given our samples F. This is the probability that we would get this F or higher by chance in this probability. So given our samples F, actually it would be easier if I wrote it the way that I said it, probably. Yeah. So the idea is the probability, the false alarm probability given for F values, right, F statistics that are equal to or more extreme than our sample F, right? Than the F from our sample. So the probability that we would get an F greater than the one that we got, right? So F from the sample. Right? So this is the F value once we have our sample statistic. This is the F value that this is the probability of false alarm that we're willing to tolerate, right? So it's the same idea as T statistics, the alpha and the p-value in T statistics. We're just now applying it to a slightly different looking distribution. All right, now on to our examples. Why does the F distribution stop at 0 but go on in the positive direction until infinity? Well, we know why it stops at 0. The F distribution is a ratio of two positive numbers, right? And we know that they're positive because variance is squared, right? Thus making it always positive, right? Always going to be positive. But it goes on until infinity because there's no rule that says you can only be this much bigger in the numerator than the denominator, right? So the numerator can be like infinitely as big as the denominator, right? So it could go on forever and ever and ever. All right. Example 2. In an F-test, also called a one-way ANOVA, which we're going to talk about in a little bit, the p-value, so let's say you did an F-test, and the p-value is 0.034. What is the best interpretation of this result? It is plausible that all the samples are roughly equal. Is that what it means? Well, let's think about it. So here we're thinking about, let's say, 2 samples, and we need this versus this, right? So the F value is between variation over within variation, right? And if we have a big F value, right? So let me draw my F distribution. If we have a big enough F value, so sample F, then we can have a small p-value, 0.034. Right? So, is it plausible that all the samples are roughly equal? No, because we seem to have a large enough between sample variance, right? So I would say no to that one. It's plausible that all the samples' variances are roughly equal. Well, that also is not necessarily what this means. It could be that these within variations are very similar to each other, but that's not what this p-value is talking about. The within sample variation is much larger than the between sample variation. Well, if that were true, we would have a small f. Instead, it's this one. The between sample variation is much larger than the within. So D is our answer. All right, example 3. Consider the heights of the following pairs of samples. Which will have the largest f? Which will have the smallest f? Okay, let's think about this. So players from NBA team Lakers versus adults in LA. Well, if we drew those two population, right? Lakers versus LA, right? This probably has a lot of variance, right? A lot of variance here because that's a lot of people. This probably has a very, very small variance, right? But there's probably a pretty, some sizable difference between those two groups of people, right? Like average adults versus like the Lakers, who are probably all amazingly tall. Well, so that's the picture here. Will this have a large f? Will it have a small f? I don't know. Not yet. Well, what about adults in San Francisco versus adults in LA? Well, these two probably both have a lot of within sample variation. There's lots of adults in San Francisco, lots of adults in LA. They're all different from each other, right? But their averages should probably be similar, right? Because it's not like San Francisco is known for super tall people or LA is known for super tall people, right? So this difference between the groups will probably be very small, but the within group variability will be very, very large, right? So I would guess this would have actually a pretty small f. And what about this one? This one is players from an NBA team, Lakers, versus players from another NBA team, the Clippers, right? And so here we might think Lakers, Clippers, right? And there's probably a pretty small variation here. Probably everybody is like above 6 feet tall, maybe even taller, right? Above like 6'4" or something, right? And so they're probably all like super tall, so there's not a lot of variation. But they're also probably similar across the teams too, right? So because probably the average height on the Lakers is probably similar to the average height on the Clippers, just because they're both super tall groups of people, right? So which ones of these will probably have the largest F? I'm guessing the biggest difference between the groups might actually be this one, right? So I would go with this one, given that I'm not really sure about the variance here, right? The variance is smaller, but I'm not sure how to compare these so far, right? So this is for largest F, and I'm just going to go by having the largest numerator for sure, right? Well, which will have the smallest F? I would say the smallest F would probably go with this one. Because not only does it have a small numerator, but it has an extremely large denominator, right? So I would say this one would definitely have the smallest F.